This video lecture is something of an introduction to some topics that are very real physical phenomenon that we're going to explore in more detail later. But these are sort of natural next steps in the development of the quantum physics of an atom. So so in particular, I really want to talk about experimental evidences. And so when we talk about evidence, you're going to see that the evidence is going to come from looking at light, right, which we can see. And this light is part of the emission spectrum of the atoms. So that's one piece of experimental evidence. But the other piece of experimental evidence is actually space quantization. The fact that the magnetic dipole moment of these space quantized physical scenarios can only ever be sort of seen, right, or spatially distributed in this quantized way. So I just want to present a few items of experimental evidence, and they have some special names. So the first thing that I'm going to talk about is called the Zimon Effect. And then after that, I'm going to talk about something called fine structure. And then after that, I'm going to talk about something called, that's referred to as a hyperfine structure. These things right here are examples where the experimental evidence for them is you actually see it, right, in the light of associated with the emission spectrum. And the explanation involves these facts right here. So the quantum theory of atoms have a prediction for quantized energy levels, and the differences in energy between various energy levels gives rise to the energies of the photons, or the spectrum, that is emitted from these atoms. Something about angular momentum, which is described by the orbital angular momentum quantum number, and the space quantization, which is the conventionally the Z component, or the m sub L quantum number, right, is going to explain actually the Zimon Effect, and also, well, actually, so the Ziemon Effect is actually explained just from this part. But then, if you want to understand fine structure and hyperfine structure, you have to include spin. So in a sense, doing experiments where you can see these phenomena, which are very, very different, you are realizing, you are sort of seeing evidence for the interplay between all of these various topics, all of these various quantizations. All right? And then there's a final sort of piece of experimental evidence referred to as the Stern Gerlach experiment. And I put a dash between these two different names because they're two different people, right? So Gerlach really is the experimenter. I think Stern came up with the idea, and Gerlach actually successfully created an experimental situation and an experiment and a procedure and an apparatus, right, to sort of carry out Stern's vision. Okay, so anyhow, so let me explain. We're going to start with the Zeeman effect, the sense in which you see it. So here's the idea. So let me move on and write Zimon. So the Zimon Effect. So here's the idea. We have some sort of a container that contains just little hydrogen atoms. And if you agitate the hydrogen atoms by running an electric current, like electrons through there, then these hydrogen atoms get bumped into and become excited. That is, they collect up internal energy. And the way that they get rid of that energy is through spontaneous emission of photons. And those photons actually go in all directions, right? So the light coming away from this thing, it's just glowing, right? So light's coming away to the left and towards the right, and it's actually coming out of the screen, and it's going back into the back of the screen, right? Light's going in every direction. It's spontaneous emission, random directions. But what's interesting is if you were to take some of this light that's coming away, you know, it's emerging, it's coming away from basically the axis of this container. And what you do is you imagine only paying attention to a small bit of the light. So you create this little telescope, and so you take it in, and so this light's now coming through sort of radial, and you actually run it through a prism. So the prism's orientation is kind of strange. I'm gonna orient it this way. So it's a prism. And this light hits the prism and is actually spread out. Right? So there's many different angles. And the light that shows up over on this end is more purple, and the light that shows up more on this end is more red. And you can look at this light, see it, right? And if you look really, really close at this light, what you see is, right, so I'm imagining these lines showing up. So if you look at it, you get things like this. You get, you've seen pictures of this in your textbook, I'm sure, but you get a red stripe, and you get a yellow stripe somewhere. You might get a green stripe somewhere, and then you get a blue stripe. Oops. And then a violet stripe somewhere. So that's all well and good, no big deal. And this is what you get for sure, right? Actually, let me be really careful. For hydrogen, you don't necessarily get this particular set of colors. And I also want to be very careful to say that in between those colors is actually no light at all. So I'm going to draw like a grayed out background, because there is no colors showing up anywhere else. It's these very vibrant stripes is the idea. All right, so in between this red and this yellow line is darkness. There isn't any color of light that's emitted spontaneously from this little gas of hydrogen atoms that's in between this red and this yellow. It's only the red, and then a bunch of frequencies that aren't emitted, and then all of a sudden there's yellow, and then a bunch of frequencies that's not emitted, and all of a sudden there's green. And there's even ultraviolet that you can't see, and far ultraviolet that you can't see, and infrared and radio that you can't see as well, right? So anyhow, this right here is the spectrum. Right? And it's the emission spectrum. It comes from these excited atom systems, these little excited sort of emitters of radiation. Okay, so I haven't shown you the Zeeman effect yet, though. This right here is just evidence of quantized energy. Right? So this is evidence of quantization of energy. That's what you see here. But the Ziemon effect is really interesting. You get the Ziemon effect if you take this sort of gas of atoms. So let me just highlight it by using a highlighter. I meant to highlight it. So you take this thing and you just move it so that, or you surround it so that there is a magnetic field. So I'm going to draw a big old horseshoe magnet that's very strong. And here, say, is the north pole of the magnet and the south pole. So in between the pole faces, there are, I guess I'll just keep it in black. There's magnetic field lines, right? They point from the north pole towards the south pole on the outside of the magnet. And what you do is you actually take this thing and you put it in between the pole faces. So I'm going to imagine putting that little gas of hydrogen atoms, those are H's, right, in between this strong external magnetic field. And then you inspect the light that comes from, that is part of the spectrum, right? So you inspect the light, you use the same apparatus, you have this little telescope that isolates a column of the beams coming out of there, right? So they're all headed in the same direction. You run it through a prism, just like before, right? And so the light that comes into the top corner of the prism gets spread out into its colors, right? And you inspect the colors that show up on here. And what you can find can be really interesting. So let me show you an example of what could happen. This green line, which when we didn't have a magnetic field, that green line was a single thin line. The Zimon effect is that green line turns into 3. And this is called a splitting, for obvious reasons, right? Right? So these are indicative of energy level splittings. Jeez. Right? And this is what is known as the Zimon effect. The Zimon effect is noticed in the fact that E sub n is no longer the only issue for energy, right? What's interesting is the way physicists talk about this is, for example, for, say, n equals to 2, just as an example, right? We know about some quantum numbers. The quantum numbers are, so L can either be 0 or 1 in this case, and in the case where L is 0, M sub L can only be 0, but in the case of L equals to 1, M sub L can be 1, 0, or minus 1, right? And that's all to say that there are 4 states of n equals to 2. And those 4 states of n equals to 2 produced one of these color bands, is the idea. So it's actually, the color bands are based on a transition between 2 different states, right? So it's the difference in energy between 2 states. So it's a slightly more complicated issue than that. But the point is these were degenerate, remember that word degeneracy, in energy. But the Ziemon effect says it's basically this. A B field tells you the difference between the principal quantum number states. That is, the degeneracy is lifted, right? So the degeneracy is gone. We can tell the difference between the various quantum states because of the background magnetic field. This small extra energy that leads to the extra frequencies, right? So I'm talking about extra frequencies because if you look at these three lines, actually the middle line corresponds exactly to the old line, right? That's the old line without a magnetic field. When you add the magnetic field, that line is going to stay there. It's not going to be as bright because of conservation of energy issues, but there are now three lines. So there is the old frequency, there is a slightly higher frequency, and there is a slightly lower frequency, right? I say the low is on the left because, yellow is a slower frequency than green, and red is an even slower frequency, right? Longer wavelength, but slower frequency. So, yeah, so I've got this splitting, I've got multiple frequencies, and I've got multiple frequencies because I have small extra energies, right? For the Zimon effect, there's a special piece of language. We say that the atom's magnetic dipole moment, right? This is mu of the atom, is coupled to the external B field, right? So we say that the magnetic dipole moment of the atom, which is a quantum mechanical, right? It's got a space quantization aspect to it, is coupled to the external magnetic field. Coupling means there is an energetic interaction, right? There is energy in the relationship between mu and this external B field. When I started off talking about just the spectrum, spontaneous emission spectrum of a hydrogen atom, when the external B field was equal to 0, right? Because there is no magnet out there, there is no coupling, right? There is no extra energy, so we don't see splitting over here. But when we do turn on the magnetic field, there is coupling, there is extra energy around, and we get to see it in the spectrum. Space quantization makes it so, even though we get this splitting of energies, the splitting of energies is actually really well defined with darkness in between. And the reason I say that is because we don't get a smearing out of the green line. What we get is three distinct lines. And that's got to do with the space quantization aspect of the magnetic dipole moment, right? Okay, so here is a new word that you're going to learn how to use in the context of physics. It's coupling. Coupling means there is an energetic interaction. So that brings me to be able to describe what are these other structures, fine structure and hyperfine structure. So the fine structure, I'm just going to describe what the coupling is. The coupling is between the magnetic dipole moment of the atom and the magnetic dipole moment associated with the spin of the electron. This is called spin orbit coupling. And this is not a minus sign, it's a dash, meaning we're coupling these two issues. So the spin is going to give rise to a magnetic dipole moment associated with the spin of the electron, and the orbital angular momentum gives rise to an atomic dipole moment. And these are two magnets, right? These are two magnets close by. And you know that a magnet feels that it can have a potential energy associated with its relative orientation compared to another magnet, right? So here is an energy that's going to give rise to further splittings in the spectrum. This right here, if you want to go and do a little bit of reading beforehand, this is responsible or is explained by the famous sodium doublet. What's interesting is in the Ziemon effect, we can turn off the magnetism, right? We can either have the magnet or not. But over here in the fine structure, we can't turn either of these issues off. The magnetic dipole of the atom is just based on whether or not you're in SPDF, right? Orbitals. And the magnetic dipole moment of the spin, or of the electron, that's associated with spin, and spin can't go away because electrons never do not have spin, right? Electrons always have spin because that's one of its qualities. Just like the fact that it has a mass, a particular value of mass that doesn't change, and a particular value of electric charge that does not change. So the magnetic dipole moment of the electron does not change, right? So these are two issues that don't go away. They've always been here in the universe. And the way you see it is actually pretty cool. Like, so if I have, let's pretend that I'm looking at the spectrum of sodium. If I look really close around where the yellow line is going to be, what I'm going to see is I'm going to see a single yellow line. But if I look even closer, so let me zoom in on this piece of the spectrum coming from a sodium gas. So if I was to zoom in, I think I went the wrong way with this opacity thing. Yeah. So if I zoom in and look super close at this yellow line, what you will see, and what was always there, you just didn't notice it because you weren't looking close enough. Oops, I guess that's not great, actually. Let me do it this way. So I'm looking, so this is the darkness in the spectrum, but if I look really close, oops. Sorry, this is sort of a clumsy presentation, but that yellow line is actually, wow, that's, okay. This note-taking thing is kind of bumming me out. Let's see, I'm gonna start over again. So eraser. So you're looking at the spectrum. And if you look real close, there's actually two side-by-side lines. You know how, like, if you look at something far away, if you're far enough away from two details that are close to each other, those two details blend together. There's no way to avoid it. They're just too close together and you're looking at them from too far away. So those details blend together. This is a blended together yellow line. But if you figure out your optics well enough, And there's tricks to use to look really close and look at the detail, look at the structure, look at the fine detail, and you'll notice this fine structure. That is, you can see it with your eyes, right? I mean, with the help of some special optics. But this right here, you might say, is experimental evidence of spin, right? We already have experimental evidence of quantized angular momentum, and the Zimon effect is quantized sort of atomic system angular momentum. So we already have evidence of that. That's what the Zimon effect shows us, and quantization of angular momentum explains the Zeeman effect. But this right here is a mixture of something we already know about now and something we didn't know about, called the spin. So you might say that this is evidence of electron spin. So continuing, what about this other issue called hyperfine structure? Hyperfine structure is an even smaller energy difference. This was an energy difference, these are two different frequencies, say F1 and 2. That frequency difference is actually kind of small. Well, it depends on the strength of the magnetic field, but it will be small compared to the splittings that happen because of the Zeeman effect, right? The field values, you could imagine putting 6 Tesla fields or something like that, which is a gigantic magnetic field. But you can cause quite a large frequency difference between the split levels. So over here, though, you don't have any control over any of the details. The electron's got a certain spin, your atom has a certain swirl, and there is a certain coupling, right? That happens. It's given to us essentially by the strength of mu naught and the amount of charge associated with E and the size of the atoms, right? So those are the details that go into. So we don't actually have control over how far apart these frequencies are. In hyperfine structure, we know that the electron is a little spinning creature, right? So there is a spin magnetic moment for the electron. But for the hydrogen atom, right, the nucleus is a proton. So the electron is negative and the proton's positive, but this proton can also have a spin. And it's actually also a spin half creature. Or let's just say it's got spin. So we can talk about the spin of the proton and the spin of the electron. And there is spin-spin coupling. And spin-spin coupling is an energetic interaction that gives us really really fine structure to the spontaneous emission spectrum. This is also something that you cannot get rid of, or you cannot cause to be worse, right? Unlike the Zeeman effect, where the Zeeman effect is stronger if you strengthen the magnetic field in the background, right? That's like a controlled variable in your experiment. Okay. So the last thing is a really cool experiment referred to as the Stern Gerlach experiment. And it's direct evidence only after you think, only after you think really hard about a bunch of stuff. It's direct evidence of spin quantization, or actually just spin and its quantization. And so here's the idea. You have these little particles that come out of some sort of source, tends to be described as an oven. It's a hot place. And these little particles just emerge, and you try to make it so they all go, or you only sort of pay attention to the ones that go along a certain direction. Of course, an oven is going to give you spontaneous values for kinetic energies and also direction of motion. So all the momentums are spontaneously chosen from some random distribution, right? Because ovens are random emitters of things. So these things, though, what you do is you try to be very careful and only pay attention to ones going in a certain direction. So these are all headed towards the right, say. And the Stern Gerlach experiment, right? It's an experiment, took these little particles and sent them through, it's really important to point this out, a non-uniform magnetic field. So the way I'm going to draw that is I'm going to make the North Pole face into a point and the South Pole face into a flat surface like this. And the reason why this is important is, and actually I should have drawn, let me move this up a little bit. So this, I'll move it up to there. So, because I want the particles to go through without touching or running into the magnetic poles. But the point is you really want a non-uniform magnetic field. So the magnetic field lines are going to be really strong near this point, and then somewhat weaker, right? The field lines spread out near the South Pole. So they're close to each other and strong on the top and weaker on the bottom. And this is a magnetic field that exists all the way through here. And remember, field lines point from north to south, so they're pointing downwards. Okay, that's the direction of field lines outside of a magnet, sort of in the open space between the pole faces. Okay, so these little things, what happens is, because the oven is understood to be the spontaneous emitter of these particles, we expect these little particles, which I want you to understand as atoms, to come out with spontaneously oriented magnetic dipole moments. Right? Spontaneous means random. So you have this random set. Essentially, if you have a lot of these things, you might say that all possible orientations of the magnetic dipole moment are represented in this beam. And if all possible orientations are represented, then each of these little magnetic dipole moments is going to be fanned out in all possible directions equally, and you should see essentially a bunch of these things hitting the other side sort of uniformly distributed, or at least distributed in a sort of a random distribution. And this is what you classically expect. Because classically you expect that this magnetic field will sort of push and pull, right? It's a non-uniform field, so there is a non-zero net force on these little magnetic dipoles. If the magnetic field was uniform, then actually the net force on these dipoles is zero, right? It sort of tugs on the north pole of the dipole as much as it repels the south pole, right? But because there's a gradient in the field, or a difference, a non-uniformity, then you have a non-zero net force and you have an acceleration sort of in the direction of the field. So anyways, the classical expectation is the spontaneous emission from our random oven just puts them everywhere, right? But actually what happens is not that. What happens is you get two spots. You get a spot up and a spot down. You don't get any up here, you don't get any in between, and you don't get any beyond. And Stern and Gerlach, and I'm not sure if it was Gerlach or Stern or people afterwards, called this the up and the down. And it turns out that we can definitely imagine random orientations of these objects running through the Stern Gerlach, this is called an analyzer, right? It analyzes the orientation of your little particle. So these random orientations, this is still a good way to think about the particles on this side. But what's strange is that even though these are randomly oriented going in, the result of asking, well, where is it going to go? You only get 2 answers. And this is called a space quantization, right? And we could say the answers are up or down. So upon measurement of the direction, right, of the orientation of our particle coming in, we only get 1 of 2 answers. And this is the origin of thinking in terms of a space quantization, first of all. But if you think really hard about a bunch of different things, this implies electron spin. And it's spin 1/2. Yeah, so these are experimental evidences of quantization having to do with atoms. You can read more about the Stern Gerlach experiment, but these were actually silver atoms. So our oven was actually some space in which you could imagine a gas of silver atoms sort of being emitted out into space. So, you can achieve that just by heating up a solid piece of silver and making it really, really hot so that it boils, right? You can boil that piece of silver. Okay, yeah, thanks for listening.